Sorry, I'll just set record and start. Our first speaker is Ai-Lan Lee from Heriot-Watt University, and she's going to talk to us about gold, silver and light. So I'll hand straight over to Ai-Lan.
Thank you very much. So thanks for the introduction and thanks for the invitation to speak here today at this webinar from my living room. It's nice to sit down and give a talk for once. So what I'll do today is, rather than cover everything, I just wanted to concentrate on two particular projects, but I'll give you a brief overview of our research interests. One of the longest running projects is on homogeneous gold catalysis, and I'll talk about this particular project today, but we're also interested in palladium-2 catalysis, some photoredox catalysis, but most of our recent work is on metal-free radical reaction. Involve any catalysis, so I'm not going to talk about that today. I'll concentrate on these two. So for the first half of the talk, I'll talk about a gold project, and in particular, silver effect in gold catalysis. And then halfway through, I'll change over to the second topic, which is using dual gold and photoredox catalysis. So before I do that, I'd just like to give a very brief introduction to homogeneous gold catalysis. We tend to use our catalyst in gold-1 oxidation state, although sometimes gold-3 is also used. And its use is usually as a carbophilic pi Lewis acid. So it activates soft pi systems, carbon-carbon pi systems, such as alkynes, allenes, dienes. And earlier in my career, I did a lot of work with cyclopropenes as well. So here's a little cartoon of what happens. You have your carbon-carbon pi system activated by your gold-1 catalyst, usually cationic, and then this activates it towards nucleophilic attack, and you can have various nucleophiles attack in the anti-fashion. So how do we make catalyst then? Well, traditionally, we would make this in situ. So you use this neutral gold chloride, you react it with a silver salt, where X is the counter ion that you want in your final catalyst. You then cross your fingers and hope that this precipitates out silver chloride and gives you this cationic active catalyst in situ. And there are advantages to making it in this in situ way, because it means we can very easily tune our ligand and our counter ion, which is very, very crucial when we're trying to optimize reaction conditions for selectivity and reactivity that we want. This tuning and this fast tuning is really important. But of course, you would have noticed that there's silver in this reaction. And about a decade ago now, she and co-workers, and quite a few people, in fact, were a bit let's say they didn't think that this silver was innocent, and they coined this term silver effect, which I'll come back to in a couple of slides. But because of this silver potentially not being innocent, you can also buy or make gold catalysts that's silver free. So these are commercially available, and very common ones are like the Gagos catalyst and echeverin catalyst. In some of these, you'll see that acetonitrile is used to stabilize your gold catalyst. Some others are not stable and you have to make it the in situ method. Now, in reality, most organic chemists might use a mixture of both of these. So here are just a couple of previous examples from our group. In this top example, we use the commercially available Gagos catalyst for our formal SN2 prime reaction. That worked well, so we went with it. But in this other project, you'll see that we needed to and for the selectivity that we wanted. So this was a hydroarylation with chirality transfer, and that was crucial. And in order to access the active catalyst, we had to use the in situ method. So we've got many projects and we use a mixture of these. So let's talk a bit more about this silver effect business then. As I mentioned, about a decade ago, this kind of conversation started. And in general, people started seeing rate differences between the ones made in situ with silver and the ones where it's gold only. And they coined this term silver effect. And then, as you can see from the selected literature, there was a bit of a tug of war and toing and froing between two camps. One that said, yeah, I saw silver effect too. I see differences in rate. And the other camp that said, nah, that's a load of rubbish. I don't believe that. I don't think so. We need to do our controls correctly. So let's call it a lively debate. And then towards the end, this culminated in this paper in 2015 by Zanko and Meyer. They did some really rigorous studies to prove that none of the ones that they showed before were real silver effects. And they very helpfully did the experiments to classify why people were seeing rate changes. The first reason is because of incomplete halogen exchange. So you need this to be complete for it to be comparable. But it depends on solvent. So if you use the wrong solvent, this is incomplete. That's why they saw rate differences. The second classification is poisoning by. So when they were comparing the in situ silver method with pure gold, they were filtering the silver off using sea light. And it turns out that sea light was poisoning the gold catalyst. That's why they saw a rate difference. And the final reason is to do with that acetonitrile that I mentioned. So they were sometimes comparing the gold only that has acetonitrile with the silver in situ method, which doesn't. And they concluded in this paper that it's due to the negative role of acetonitrile that changed the rates and nothing to do with the presence of silver. So that clarifies the matter. But you can actually genuinely see rate differences. And this was the experiment they did, and this is the conclusion. You have your standard gold-only catalytic cycle, so a generic hydrofunctionalization, and the silver doesn't really mess up your gold catalytic cycle. What it's doing is that it can potentially form this off-cycle intermediate in equilibrium. So it doesn't affect the cycle, but it affects the fraction of available organogold species, and that is why it affects the rate of your reaction. But they concluded in this paper that a true silver effect, meaning one that affects the actual gold catalytic cycle, has so far not been discovered. And we thought that was the end of that story. And we thought, okay, we'll draw a line under this. That's the end of that. But meanwhile, in Scotland, my postdoc was trying to make this molecule here for synthesis. So we're going to go on and do, I think, dipolar cycloaddition. So obviously, we used Gold-Catalysis. We're trying to do hydroaminations here. And he did some really extensive optimization. I'm just going to show a snapshot of some of the work. And he saw something really interesting. When he used silver with gold, so this is the in situ method, he saw actually this 6-endo-dig. When he used potassium carbonate instead of silver, it switched over to the 1Z5-exo-dig. And when he used sodium or cesium, he also saw only 5-exo-dig. So it's only silver that was giving the regioselectivity switch. And you have to use them in situ. Using just gold or just silver gives you no reaction at all. So I told him to stop what he was doing because I thought this was quite interesting. It seems like the silver counter ion might be responsible for switching the regioselectivity between 5-exo to 6-endo-dig. So the first thing we did was to just study whether this is a one-hit wonder or whether it's a general thing. So we made several of these terminal alkynyl sulfamides. So they're all terminal in this table, and it is general. So by and large, with method A, with potassium, you'll get 2. And when you switch over to silver, you will get 3 by and large. But we only saw a big difference when we moved away from terminal and put a substituent there. Then the scenario totally changed. So when we have a substituent here, we now see that regardless of whether we use silver or potassium, we now see the same ratio and favoring 6-endo-dig. So based on these results, we came up with our initial hypothesis for what might be going on. We thought we were quite clever at the time, you'll see. So we originally thought, okay, this one is favored when it's blocked. So we think that the 6-endo-dig came from pi activation only. So this is what you usually draw as the activation intermediate, just on the back of an envelope. And we thought this because whether I block this position or not should not change the outcome. So that's why we think this gives 6-endo-dig. Whereas the 5-exo-dig no longer is favored when you have got a substituent there. So we suggested that this comes from the sigma pi digold acetylide instead, and it requires the terminal alkyne to form the gold acetylide. So we had to check out our hypothesis. And what we did was to make a terminal alkyne again, but this time with a deuterium there. And when we subjected these to the conditions. So on the right-hand side, going to the 5-exo-dig using potassium carbonate. Remember, we suggested this came from the digold acetylide, and if it does, the deuterium should not be in the product because it goes via this intermediate, and that's exactly what we see. So that was great. But we thought that this product 3H here comes from the pi activation only. Now, if that's true, then this deuterium should end up in the product, and we saw none of it at all. So it's not pi activation only at all. We think that the pi activation only occurs if you have this position with the substituent, so internal. And that's why with internal alkynes, we saw no ratio difference between the methods. But for this, we think what's happening is that that does come from what we suggested, but that the 6-endo-dig instead comes from a gold-silver acetylide, because we only see that when you have silver in there. So this was the suggestion. So before I go on to my mechanistic studies, let's have a look at the proposed mechanism. You have your neutral gold. You extract out chloride to form the gold, cationic gold, the alkyne, like so. And in turn, this alkyne proton much more acidic. So you can easily take that off and form this key gold acetylide species. Now, if I don't have silver in there, then gold will come along and activate this, and we do our hydroamination, and it forms 5-exo-dig. And presumably, if we have silver around, silver can instead activate our alkyne, do the hydroamination, and form the 6-endo-dig instead. Now, to test this, we of course had to try and make this key intermediate. And after several attempts, we finally got there. So that's the crystal structure of the Josephus intermediate. You can see the nice linear structure of gold 1 there. We then subjected this to stoichiometric studies and monitored it using proton NMR. So this is that key intermediate I just showed, the gold acetylide. On the right-hand side, we subject this to stoichiometric gold. So let's look at the NMR in green. This is the NMR of clean number 5, the gold acetylide. In yellow is the NMR of clean isolated 2H. So this is made separately. And in purple, that's this exact reaction. So you can see that it's forming 2H, so because it maps on very nicely. So that seems to follow what we think. And then now on the left-hand side, at the bottom here, we have in blue, clean isolated 3H that we made separately. In red, we have this reaction where we subject the gold acetylide to silver instead, stoichiometrically. And you can see it's slightly dirtier, but you can see it again does map on 3H as the major product. So it does seem like this intermediate subjected to gold gives you 5-endo-dig, exo-dig, subjected to silver, and you get 6-endo-dig. Now, why it changes and switches regioselectivity, we really are not sure. We don't have answers for that yet, but experimentally, it does really seem to go that way. So just to summarize the first half of my talk, it was about the silver effect. We showed the first example of silver-induced switching of regioselectivity in gold-catalyzed reactions. Usually, it was mainly just a rate change. We also think it's the first mechanistic evidence to suggest a first true silver effect, so one that actually messes up your gold catalytic cycle. And then finally, it also means more generally that when you have terminal alkynes like that, you maybe want to be careful when you're using silver, though in our case, it was kind of happy result for us. So thanks to Marcos, the postdoc who did all of this work. And I'll now move over to the second half where I'll talk about dual gold and photoredox catalysis. So before I do that, it's probably useful to explain why we want to do dual gold and photoredox catalysis by explaining what conventional homogeneous gold catalysis is like. So it's traditionally isohypsic, meaning it doesn't cycle between its oxidation catalytic cycle, unlike, for example, palladium and all these other metals that we know and love. So here's again a cartoon of what usually happens. It activates nucleophilic attack, anti-fashion, and then you get a proto-demethylation. Now, after many years of the gold field developing really beautiful reactions using this traditional chemistry, we then got a bit greedy and said, it's nice that gold can do that, but won't it be nice if gold can also do what palladium does, meaning cross-coupling? Can we intercept this organogold intermediate and force that to do a further cross-coupling, so you get 2 in 1. And indeed you can. But as I said, this doesn't usually cycle its oxidation state. So you in a stoichiometric oxidant such as select fluor to get the cross-coupling to work. And this is beautifully reviewed in this review here. And then further from that, after a few years, we went, oh, that's very nice. So that's proof of principle. We had to show that. But in a way, when you ever listen to a homogeneous gold catalysis talk, we usually go on about how mild the reaction conditions are. It's very functional group tolerant. You don't need dry solvents. You can do it in air. It's really quite cowboy chemistry, and organic chemists love that. Chuck it in, stir, it works. But if you use stoichiometric oxidant, you've lost some of that mildness. So we wanted to come up with a catalytic and milder version to do this. And this is where the dual cycle comes in, because your photoredox cycle helps to get access that Gold-1, Gold-3 cycle. And it was Glorious and Toast that pioneered these dual studies. Now, our foray into this was a bit kind of through serendipity. It all started with this particular project, quite some time ago now, where we were trying to use boronic acids as nucleophiles in our gold reactions, but instead found that this can transmetallate if you have water in there. That's just like, you know, from the air or undried solvents, because I said we're a bit cowboy about this when you're an organic chemist. And then we got the intermediate here, which initially we just proto or deuterodeboronated. And that got us this ridiculous cover in JOC, which the rain clouds were supposed to signify the Scottish weather, although I should say it's a beautiful sunny day at the moment. And also that it needs water to assist this transmetallation. And it was my computational colleague, Stuart McGregor, who kind of did the studies for that. Then we wanted to challenge this further. Can we trap this with other things? We can. So one of the other things we did was to trap this with iodine instead. And together with Andy Sutherland, we showed that we could use this for radio labeling, radioiodinations, and make radiopharmaceuticals using this gold method. And finally, we wanted to do carbon-carbon cross-coupling, so challenge ourselves even further. And that's why we started looking at photoredox. So by using the photoredox cycle in dual fashion, we were able to intercept this and use a coupling partner and get our cross-coupling. But that's not what I want to talk about today. I want to talk about what happened next, which was we wanted to challenge ourselves to try CH activation. Now, when we say CH activation, you're probably mostly thinking palladium, ruthenium, rhodium. Why gold? There are a few things going for gold, few advantages. And the main one is that word again, mild. How mild, I shall tell you in a minute. But the main benefit is this. It's regioselective without directing groups. So it doesn't need chelate-assisted directing groups like a lot of the other transition metal ones do. And the reason why it can do that is due to the mechanism. So when you have an electron-rich arene, this can do electrophilic auration with an electrophilic Gold-3 species, and you form this Whelan-type intermediates, which allows it to be ortho-para-directing. So that's why you have Karash, of course, did this stoichiometrically in 1931, but much more recently than that, people have used this for catalytic studies. But I'm mainly interested in carbon-carbon cross-couplings here. So let's see what are some of the seminal work in this area. So here are just some of the beautiful papers in this area. And the seminal work was by Guy Lloyd-Jones and Chris Russell in this beautiful work that was published in Science. And they showed that these electron-rich arenes can react with aryl silanes and do a CH activation cross-coupling with a stoichiometric oxidant and an acid. Now, what was so groundbreaking about this work was what I said before. You did not need chelate-assisted directing groups, yet it was regioselective. So if it's so good, then why is it that us general synthetic chemists haven't quite adopted it more widely yet? And the reason is we think these two here, which was summarized in this review on the topic by Kramer. Firstly, it's the limitations in arene scope. In all of the papers, you will find that the arene has to be very specific in electronics. And often the two coupling partners have to have very specific electronics for it to couple well. And I'm afraid I did nothing to address that particular limitation. So it's still something to be addressed for the field. But the second limitation was the one that we were trying to address, the use of stoichiometric oxidant to access that goal-1, goal-3 cycle to do cross-couplings. And we do CH activation, usually we're explaining that it's greener, we miss out a step, less waste. So obviously the next kind of way to go forward is to try and get rid of this excess waste that will come from having stoichiometric reagents in there. So obviously, based on what we did before, what we were trying to do is to exploit the dual gold catalytic and photoredox catalytic cycle again. So this was the plan. And the reason really why we wanted to do that was because it hadn't been done before, and mainly as proof of principle to show that you can do gold-catalyzed CH activation without stoichiometric oxidant. So let's see how this went on. And very unusually for one of my ideas, it worked first time. The postdoc was rather shocked. So I'll talk you through what's happened. This is the arene that we used in the model study. This is the coupling partner, gold catalyst, photoredox catalyst, and we shine a blue light on it. And you see, almost immediately we had a hit. So that's really not bad for a first try. Usually it's 0, 0, 0 for quite a while. And then by our third entry, we got to a decent yield. And we're quite happy that we only needed 3 equivalents, at least for this model substrate. Because in many of these, where you don't have directing groups and you try to do CH activation, often a severe excess of the reagent may be necessary. So 3 is considered really quite good. You can use cheaper organic photoredox catalysts, but we stuck with ruthenium for now, and upon optimization, got pretty good yields of the cross-coupling partner. So let's have a very quick look at the substrate scope. The diazonium pretty much worked the way we wanted. There's no surprises there, so I won't go into it in much detail. But the arene, that's the one that's used, and ours was no exception. You will see in the whole host of substrates here that they are all overall electron rich, and that's expected from the mechanism. But on top of that, we needed it to be slightly electron rich. It's very regioselective, so that's good. I'll talk a bit about that in a second. You can have withdrawing groups, so that's not a problem. It's just that the electronics overall of the arene has to be slightly electron rich for the auration to take place. What we were disappointed about, so all these worked well, was that the very electron-rich ones did not quite work, but mechanistically it should have. But it was because we had a side reaction of diazotization. Apparently it's a beautiful purple dye, it's 1970s chemistry, very pretty, but no good for cross-couplings. So there's a slight limitation there. However, there's no such version. So these are very electron rich and they work well. But more importantly, there's no oxidation at the sulfide or the benzylic positions. And these are very oxidizable positions which may not have coped with the harsher stoichiometric oxidants. So it shows how mild these catalytic conditions are. And then finally, the regioselectivity, I mentioned that it is very reliant on the gold. So if you take the gold out, the reaction still works, but you get a horrendous mixture of inseparable isomers. This is no good for synthesis if you can't separate them. And this is a known procedure. So we tried the literature procedure. You'll see it pumps up to 40 equivalents. The yield goes up, but still it's a isomer. So the gold is necessary for regioselectivity. So that's my last chemistry slide. Just a proposed mechanism. We think that we start here with the gold-1. Your arene radical that comes from the diazonium salt adds on to get you gold-2, which quickly undergoes a single electron transfer to give you this key gold-3 species, which then gets attacked by this electron-rich arene. That's why it has to be rich. You get a Whelan type intermediate. That's why you see regioselectivity, and then reductive elimination gives you product. We did stoichiometric studies and we saw evidence for this number 6 here, which comes from reductive elimination of this key species. And you only see that when you shine a light so far. So just to summarize, we were successful in this. It was the first CH activation using a mild and a catalytic oxidant. So thanks to Vincent and Dan who did this work. And Dan, when he graduated, gave me this gold cat as he says bye-bye to the Gold-Catalyst. So thank you to the three people whose work I talked about today, also to the collaborators that I briefly mentioned. To the rest of the group, that's a very old photo when we were allowed to stand next to each other. These particular projects were funded by the Leverhulme Trust, but thanks also to all the other funders for the work. And thank you again for the invitation and the kind attention. Thank you.
Thank you very much, Ai-Lan. If anyone has any questions, please just type them in the Q&A and I will read them out. I have a question, and it may be a bit naive because I come from an engineering and inorganic background. I don't think I've done organic chemistry since I was at school. But obviously there's quite a big drive to reduce the use of platinum, palladium, that kind of metal. Are there any other sort of reaction schemes you think that this sort of gold photocatalyst could be investigated for replacing?
Yeah, so gold can definitely replace platinum because they're kind of the same kind of reactivity, but gold is a lot cheaper than platinum, obviously. And it has the benefit of being able to tune the ligand and counter ion, like I showed. But palladium, because its reactivity is quite different. And with gold, we can, but as you can see, we do need to, yes, put in that oxidant to force that. So gold obviously is also expensive. So I think if you're thinking about sustainability, gold is still something that will be a worry. However, it has such unique reactivity compared to the other transition metals, which is why people were interested in it.
Okay. So Michael has a question, and he says, thank you for a very nice talk. Question on your mechanism for the gold-silver system at the beginning. When you need 2 gold fragments to activate the alkene, should they show up in the reaction order in the gold? Right, okay, yeah, it should, but we didn't do the kinetic studies. I think, so I am an organic chemist background, so this was kind of about the limit of our, of our mechanistic. To do this more rigorously, we'd certainly get in touch with physical organic chemists who knew more about what they were doing to study this. But at that point, we ran out of the funding and Marcos kind of left. So this was kind of where we left it. But yes, that's kind of further study. Anonymous would like to say, when you say you have mild conditions, how tolerant to water and oxygen is the catalysis?
Sorry, what was the question? I didn't hear it.
When you say mild conditions, how tolerant to water and or oxygen is the catalysis? Oh,
very. So I think it depends on the actual gold catalyst, but most of the ones I showed you, and especially the commercially available ones, and under normal tradition, use Gold 1 all the way through, it's very, very tolerant. So we don't dry our solvents, we do this in air. And the mildness is also to do with most of these reactions being able to be carried out at room temperature. So it often, some do need heating, but a lot of them may not necessarily do compared to other Lewis acids like scandium. You'd have to heat it to like hundreds. So that's the main thing. But some of the more sensitive catalysts, then you may have to.
Okay, I hope that answers the question. If there are no more questions, I will move on to our second speaker of the day. Ai-Lan,
I'll just stop sharing if I can figure out how to do that. Oh no, there
I can do that for you.
Stop sharing.
There you go.
Thank you very much.
Beautiful. So it's my great pleasure to introduce our second speaker, Professor Fernanda Duarte from Oxford, who is an expert in computational methodologies looking at chemistry and biology, and she's going to talk about reactivity in solution and confinement. So I will hand straight over.
Okay, can you see my slides just before?
Yes.
Yeah, perfect. So good afternoon, everyone. Thank you very much for the invitation. It's a great pleasure to connect with all of you today after lunch and share some of the chemistry that we have been looking at. So this is Well, many of you are experimentalists, but I want to encourage you to, because it really is a very exciting time to be a computational chemist, maybe combining tools from experiment and computation to explore different aspects of the chemistry that we explore daily. New development in machine learning, you have heard, for example, automation and other new methodologies are allowing us to explore increasingly complex systems. And this is just I will say, a timeline of how computational organic chemistry has been evolving. You can think that we started with back of envelope models, and then we started to move in activation energies, kinetics, and later to making predictions. But actually, this timeline is far from linear, and we still see that even though machine learning and automation promise to transform experimental chemistry, we still have some challenges related to interpretability and accuracy. And in those aspects, the previous methodologies remain extremely powerful. And we see ourselves, particularly in our groups, using these back of envelope models and these early descriptors daily in our research. So what we try to really do is take advantage of the new development, but also taking in mind all the huge contributions that have been done over the years and that remain extremely powerful. And that is important to take into account because we have still many challenges in computational chemistry. We are far from reaching the full predictive tool, and we have challenges, for example, instead of solvation, entropy, conformational sampling. So even though we now can make descriptions and provide interpretation of the chemistry that we see experimentally, moving into predictions remain a challenge. But of course, we want to tackle those issues and explore chemistry. And our hope as a group is to understand the fundamental chemistry taking place in solution and in more complex environment. And we have been doing so, going from small molecules in solution to more complex reaction in enzymes. In all these cases, we're very much interested in the forming and breaking of those bonds and in developing models that allow us to first understand the chemistry and then to make predictions. For example, in the atropoisomer system that we're looking here, we're able to develop a simple model based on a steric representation to make predictions about the activation energy of isomerization. We have also been able to develop methodologies to make predictions related to supramolecular catalysis and later to study metalloenzymes. So every time that we're exploring the chemistry in solution, we're also looking into how to make that easier, more accessible to others. And an important part of our research more recently has been in computational developments, looking in new approaches to speed up the study made by experimentalists, but also by computational chemists. And in that framework, I would like today to discuss with you two main recent projects that we have been working on and that we are very excited to share. And that is related to supramolecular catalysis and reaction mechanism, very much starting in the aspect of physical organic chemistry that the previous speaker has been presenting. So in the area of supramolecular chemistry, this is something that I was introduced initially by Paul Lusby in Edinburgh, and we continue working together in this very exciting area. You have seen probably these amazing, very beautiful structures that I'm showing just 3 of them here. Those are supramolecular assemblies that just form spontaneously in solution. You have the building blocks, you mix them in solution, and they form this amazing structure. And there have been many applications related to drug release, chemical sensing, and separation. But actually, catalysis has remained one of the main challenges there. And that has been presented many years ago, more than 20 years ago, by Professor Jeremy Saunders. He pointed out the potential of those systems, but also the many challenges that we have in understanding catalysis in those systems. And that is not only important because it can be very powerful, functional and modular catalyst, but also because they may allow us to understand better biological catalysis in a biomimetic manner. So we started to explore that with the aim of first being able to develop new biomimetic catalysts, but also understanding what is the chemistry, what are the interactions required for develop new catalysts. And this process, we were interested very naively maybe in catalysis first, but as always, there is a range of different processes that are taking place before and after the process of breaking and forming bonds. And here I'm describing pictorically that a chain of events. So imagine that we have a reaction, we know the rate constant. We usually computationally explore the activation energy, but we know that there are many different aspects that will influence that reaction. In the case of assembly, we have first assembly process, the catalysis taking place, and then the release of the product being formed. And actually, one of the main challenges in supramolecular chemistry has been overcoming this step, the release of the product. Many of the catalysts that have been developed, they cannot turn over because the product inhibits the reaction. And that has been one of the main limitations. Also, the size and the complexity of the system have very much limited the computational studies that have been done in those systems, because the methodologies are not yet there to explore such complex environments. So we have been trying to contribute into this aspect with new computational models that allow us to explore very easily these reactions in solution. And actually, computationally, there are only two systems that have been explored. This one that takes place in water, CC reduction elimination, and the second one that is a reaction that has been led and introduced by the last big group in Edinburgh, and in which we have been doing the first type of computational modeling there. So this was the initial system. Very naively, we were considering that this will be a very simple cage to get started, that we could develop new cages by understanding this one. And indeed, we have started to learn a huge amount about how those supramolecular cages work. But still, this one alone was not a simple modeling study. So the question in this case was, you have this cage, general structure is this one, but if you take just one atom or two in this building block, you have different type of reactivity. In this case, we are looking at the Diels-Alder reactivity, and we saw that if this X group is a CH, so this is a benzene group, you have a strong binding, but no catalysis. Instead, if you take this for a nitrogen, you have weak binding, but catalysis is taking place. And the question was where the difference was coming from. Was not very clear at that point. So we decided to develop a computational model that will allow us to get new knowledge about that chemistry. And firstly, we started to explore using a combination of density functional theory and classical molecular mechanics. And the first insight came from looking at the electronic structure of the system. Here I'm showing the electrostatic potential, just a layer of the electrostatic potential of this cage. So imagine that we're looking at this plane connecting these two ligands here. Here is the metal at the top and at the bottom, and you can see immediately that there are differences in the acidity of the hydrogens in this alpha position. And that is very important because those very weak interactions are the ones that allow binding to take place. They may be relatively weak, but the sum of all of them, in this case, 8 different interactions, make binding very strong in the one that we call a CH cage, when we have benzene here. You also have a CH pi interaction, which enhance binding. In the case of the NH cage, just changing that single atom make a huge difference in the acidity of the system, but also in the type of interactions that you can have. In principle, you could have this charge strength interaction, but because you have a solvent, very polar one, this interaction is very, very weak. So you have a much weaker interaction. And that allows us already to explain why the differences in bindings are observed experimentally. But there is also something about the sterics of the system. And that is something that we can do when we do classical molecular mechanics, and is the flexibility of the environment. Just by changing this group here, we see a large change in the flexibility of the cage, which we are measuring here based on the helicity. So if we try to switch the cage in this case and form a helical structure, we see that for the end cage, that is much more easier, that can populate much more different regions of the molecular space. And we will see that actually this one is very important for catalysis. So with that model, initially understanding binding, the origin of that binding, we're able to develop a very simple methodology that in 8 hours will allow us to calculate binding for different substrates. In this case, we're considering a different type of set, and with this methodology, we're able to get a very good correlation. You may think that it's still very poor, but it's quite high compared to the type of correlation that you when observed for very small molecular systems. Decided, okay, we can understand binding and we can have a methodology to calculate binding accurately. What about catalysis? We're able to model the reaction, and indeed we obtain the differences more or less in relation with the experimental data. As you can see, we're calculating energies rather than free energy, but I will be very happy to discuss those approximations that we have made there. But the question was, where is that difference coming from? And to explain that, we decided to use the so-called distortion interaction activation model, which allow us to split the activation energy in two terms. One is distortion, and the other one is the interaction. So distortion is telling me how much energy I need to distort my system from reactant to the transition state. And the second one is the stabilization that my catalyst is providing into the system. In both cases, you can see that the catalyzed reaction compared to the uncatalyzed is very asymmetric, because you end up having a negative charge in this case that is stabilized by the CH interaction that I was showing before. So we decided to carry out this analysis, and we're comparing the distortion between the CH cage and the N cage. And if you see each of the building blocks, the diene, the dienophile, and the catalyst, they all have some distortion, but it's not huge. Diene is the main distortion. But actually, we later realized that this model was not the best one to explain, because in fact, what we have initially is a complex that is stable and to which the diene will add from this side of the cage. And actually, the distortion that you see going from reactant to the transition state is quite large, and is significantly large for the CH cage. As you may remember, I mentioned that that one is much less flexible, and therefore the penalty to distort that complex is large. With that system, we can see that actually this distortion of the complex is the more significant, making the difference between the CH and the N cage, and almost completely provide the distortion required for the reaction to happen. So we're able to explain why the CH gate, in this case, a lack of flexibility, a much larger penalty, hindered the reaction. And indeed, with a very simple methodology, again, we're able to explore in very few hours, identify reactions that may be catalytic or non-catalytic. We didn't have any false negative, and therefore provide us good basis to start applying this methodology for new systems. But again, looking at that system, we were manually doing everything at that time. 150 atoms, drawing them was quite painful, so we decided to introduce automation in that case. And we did that through this graphical interface that we have developed, where by only introducing a smile representation of your building blocks, you can draw in a few seconds the cage that you want, you can obtain the electrostatic potential, and you can also introduce a substrate in the system, identifying that if it will bind or not. I'm showing this for the palladium 2Al4 cage, but we have developed that for a range of different architectures. So that is making a much more efficient approach of exploring really and discovering through computational chemistry new supramolecular catalysts. But there was another challenge that led us to the second aspect of the second part of the talk that I wanted to present, and that was to study transition states. So we were able to develop cages and identify which one will bind, which one will not bind. But what about catalysis? We were still doing the work of manually looking at the potential transition state pathway. So that was quite painful, and we decided to introduce automation in that way too. And that was done through a new program that we introduced that we call autode, developed by these students in the group led by Tom and Joe in particular. So this is not new. Many people have been trying to introduce automation in reaction pathways, and there have been maybe two main approaches for that. One is the single-ended method, where you say, computer, here I have a molecule, tell me all the different pathways that I can explore. And the second approach is a double-ended approach. When you tell the computer, here is the reactant, here is the product, tell me the potential pathway that can connect those two steps. And we decided actually to take this second approach because we think that as computational chemists, as chemists in general, we're able often to draw at least a representation of how we think the pathway will go. We can very easily eliminate some unlikely pathway. So we thought that we could use that knowledge to optimize the process of a computational reaction mechanism. But the known models had several limitations. One of them, that was the main program available to do that, you have to pay quite a large amount of money that we didn't have. The second one was the limitation related to conformers. You don't have any conformers. And we know that for flexible systems, that is hugely important. And the third one was that those programs available were not suitable for transition metals or for any complex molecules that will be far from the standard organic molecules. So we decided to introduce this program. We call that autode, which is based in this double-ended model, but aim to introduce much more functionalities related to conformational search and also to extend that to organometallic reactions. So I will briefly show you how it works in practice. This is not a graphical interface yet. Hopefully we'll reach that point. But if you're familiar with some basic scripting, you can use this. The input file will be a smile representation that will tell you the reactant and the product. In this case, is an SN2 reaction. The reaction is taking place in water, and you ask the program to calculate the reaction profile for you. And as output, you will have this energy profile. So what the computer is doing during these 30 minutes is calculating the conformer for the reactant and the product independently, optimize them, then locate the transition state, also find different potential conformers for the transition state, and calculate single points. You can also ask the program to calculate complexes that may be lower in energy than the independent species. So that is the practical aspect, but actually the philosophy behind that is particular how you find a transition state is by using graph representations. And this is very much what we do when we draw chemdraws. So we have a chemdraw, in this case of this reaction, and we want to tell the program, please find a transition state for me. So what the computer will be doing is first using this chemdraw representation, convert them to smiles. Then from the smiles, you can generate a graph representation and identify the bonds that are being formed and broken. So in this case, you count all the bonds, all CC, CO, CH, the same for the product, and then you identify the bonds that are being broken and the ones that are being formed. And that saves you a huge amount of time because then you don't need to explore all the potential combinations. You just explore the ones that you know are relevant. And then we do several combinations to identify which represent we call that isomorphic, meaning that will be directly converted to the product. We can have many different combinations that break a CC bond and form a CO bond, but actually we know that it's just one, the one that is important, and that is the first one. And through that first representation, we can see identify the transition state and then very easily optimize with an electronic extractor method. We have introduced this methodology for reactions that involve the formation and break of one bond and two bonds. We're still far from reaching 4 bonds, but it's still that ability of form and break 2 or 1 bond in one steps is covering most of the chemistry that we're interested in. We can do the truncations, and we do that with systems that are quite large. So imagine that you have this large system, R is very big, and you want to identify this process. So if you, for the reaction to happen initially, you will break down and simplify the system by introducing hydrogen here, and then go back to the system. We're currently exploring new ways of calculating transition state. Initially, we have a linear interpolation where you have the reactant products, you identify the transition state through graph, you do an interpolation. But we see that in some cases that is far from true, because for example, a reaction that have a transition state here, that will be a very far starting point. And now we're trying to introduce new methodologies to make that more efficient. And here are some applications maybe for you more interested of what we can do with this methodology. I was showing you an SN2 reaction that is very easy, but actually we can do a multi-step reaction shown here. This Ai-Lan Lee rearrangement was reported in 2019 by the Stoltz group. There was a computational study by Ken Haug and Morikuma, and they mentioned that it took them a year of exploring all the potential different pathways. Of course, we didn't take all the potential pathway, but just studying one of them took us a day exploring that. And actually, we did find almost the same pathway, with the exception that we found a more stable conformer at this point. And that only required for us to draw the chemical representation in a ChemDraw and extract the SMILE structures. More importantly, we're able to show that can be applied to metal complexes. Here we draw a very simple, maybe organometallic reactions, but again, showing the power of exploring a multi-step reaction involving a metal center. Again, very short time compared to the manual exploration of this reaction. So we're very optimistic about the methodology. We still have many limitations too. This is based on a graph representation, which may limit what we call a bond, especially when we're looking at metals or imagine heavy atoms being involved there. The concept of a bond may be not quite the same as the one that we used to think about. DFT is still a huge limitation. That is the most of the time that we spend is calculating electronic structure methods. And some of the methodologies are just to describe the solvent of the environment around. So by that we want to use this for looking at supramolecular system. We still have to improve many ways how to calculate a solvent effect and larger conformational changes. And just to close, I will mention briefly what we have been working in the last few months to overcome that. And that is to avoid and really remove electronic structure methods from our calculations. Initially, we were thinking, okay, we can go to classical force field to do that are well known, very easy to work with. Or we could do a QMMM approach that is also very commonly used. But still, we have seen it's hugely expensive if we want to explore hundreds of supramolecular cages in an efficient time. So what we have been doing is developing machine learning potentials. And what that allows us is to do sampling. For example, this SN2 reaction that I was mentioning in solution, but actually doing very few calculations. And that is something that I hope I can share with you in a future presentation, much more detail about this much more recent work. Because even though we're far from applying that to supramolecular cages, we're at the point that we can calculate in few minutes or in a day, we can get an efficient simulation of an SN2 reaction in solution and hopefully of a new supramolecular system in solution as well. So with that, I think that my time has been coming to an end. I would like to finish with just some few points to consider. In the supramolecular work that we have been doing so far, we have learned how important is pre-organization, but also flexibility. And that is something that actually Jeremy Sander was presenting in his review 20 years ago. He did emphasize that we tend to optimize too much this transition state structure, and we should care about also flexibility of the system. And that is what we have been learning also more recently with the system that we're looking at. That is key to avoid a inhibition, but also to allow catalysis to take place. We have also been able to optimize the process by introducing automation in our protocols. Right now, we can draw hundreds of different cages and explore them much more efficiently than we used to do. Exploring reaction pathway remains challenging, but also we have been trying to introduce automation there. And we have seen that introducing chemical knowledge, that means telling the computer the mechanisms that we think are possible, allow us to reduce hugely the chemical space that we have to explore. So I think that that is the power of chemical knowledge has to be introduced when we are looking into automation. And then finally, there are many challenges for us to explore this type of systems in solution. Even enzymes, this hugely complex system, remain challenging for us. But we think that introducing machine learning potentials will allow us to overcome some of the challenges in those areas. And with that, I would like just to thank my group. This is a picture from last summer. hopefully this summer will be better. And they have been doing all this work in the last 2 years. So all the results that I presenting is from the work that they have been doing 2 or 3 years working with me. And thanks to all of you for listening today.
Thank you very much for a really interesting talk. If anyone has any questions, if you could type them into the Q&A box. I have a question, and it's not strictly scientific, but going back to the start of your talk, you said you would highly encourage all experimentalists to get more confident with modelling and computational methods. Have you got any resources or any routes that you would suggest other than collaboration for that? I mean, computational modelling has moved on, and what you showed to a non-computational modeler looks very complex in what you're doing here. So how would someone get started from an experimentalist point of view?
Yeah, well, now through lockdown, there have been many activities going on online. Recently, last week, there was a virtual computational chemistry winter school led by people in the UK, but also by others. So I think that going to those resources is hugely important. And finally, well, that it will be some reading. At the end, one has to dedicate time to learn something new. Something new always takes time, but in 3 months, as you learn languages, how to learn all the other things, it's allow you to really go deep into the methodology. And one way to do that is usually use your system, use the system that you are currently studying in your lab to explore that, because you can do plenty of tutorials using Python, using Orca, using all these methodologies. But really, it's when you start to work in a new system, the one that you know, for example, is that you start to realize all the challenges. But as you overcome them, you confident on that. So I think that it's in particular with Python and other languages, it's just another language that you have to push yourself, embed yourself into the exploration and failing to be willing to fail and to be challenged.
That's a good point. We have a question from Amanda Jarvis, which is, how do you see this work being applied to more complex catalytic systems such as metalloenzymes?
Yeah. Well, something that we have been very interested in doing with the machine learning potential is developing them for metals. We have done very basic application right now, but what we like to combine, and that is something that people is familiar in the communities, are those QMMM approaches. People have been using them, for example, using one part high level of theory, the other one low level of theory. Can we use, for example, those machine learning potentials to replace one of those methodologies? So I think that is one way that we will be able to explore those systems. In particular, metalloenzymes are a very exciting and challenging system. They condense all the challenges that we have. But I think that looking at these supramolecular cages is a very good learning process for us. We get so much knowledge and confidence about the methodologies, but also knowledge about how to explore catalysis. And we see that the processes are very similar to those that we'll see in enzymes later.
Okay. Are there any more questions for either of our speakers today? Just give people a few moments to type if they have any questions. Nothing's come in yet. If there is nothing else, I would just like to thank our speakers again for 2 very interesting talks. Thank you for giving up your Monday afternoon to come and talk to us. It was really fascinating. And I look forward to the future talks on the supramolecular cages and some on gold and silver and on the photocatalysis with gold. Very exciting work to come, I think. So, oh, just saying great thanks coming in on the chat from Alkynes.
Thank you to everyone.
So I'm sure everyone is giving you a round of applause. It's the hardest thing on the webinar. You can't see the audience. Chris has raised a hand. I can allow Chris to talk. Have you got something to ask, Chris? Oh, just thanks. That was his raised hand. Okay, that's thank you. So yes, lots of thanks coming in on the chat. So I will end the webinar now, but please look out for our next webinar, which is the 17th of March, and is with the Applied Catalysis group, with talks from GSK and Johnson Matthey, David Lennon, and RAW, which is the rapid characterization. So thank you very much, and I look forward to seeing you there.
Thank you.
Yeah, bye.
Right.